Okay, then. Hello everyone. So till now we have seen about CMOS inverter. Okay, so this is the basic structure of CMOS inverter, and we had seen and we had derived the important parameters that are required to define to analyze this inverter. Okay, so just a quick review of what we had seen. We had seen the VTC characteristic. Okay, and uh, this is the NMOS. Okay, this is PMOS, and this is complementary in nature. So when NMOS is on, this is off, and when PMOS is on, this is the NMOS is off. So at any given instant of time, only one of the only one of the device is available or on, and the other device is not available or it is off. Okay, so only either this the upper path is available or the lower path is available at any given instant of time. Okay, and we have seen the VTC characteristic. So this is basically the VTC characteristic, the curve between output and input voltage. Okay, so the behavior of output voltage with respect to input voltage, and this can be divided into 5 regions we had seen, and these are the various conditions for these 5 regions. Okay, and mind it, this for this particular region number C, region C. Okay, this is the region where our both of the devices are in saturation mode. Both are in saturation mode basically. Okay, and when input is low, output is high, and when input is high, output is basically low. Okay, so this is inverter, and what are the various conditions for all these 5 regions, and how to analyze this, how to decide about the mode of operation of each of these devices, that is NMOS and PMOS, and depending on their respective individual modes, then that particular current equation should be used in the analysis for deriving these 4 parameters, VOL, VOH, VIL and VIH. Okay, then we had seen that VOH is actually equal to the power supply given to the circuit, VDD. Okay, and VOL is equal to just the ground voltage or zero voltage. Okay, so this is straightforward. And then we had seen the equations for the derivation for the equation for VIL and VIH. Okay, so this is the equation for VIL and equation for VIH, and then we saw that on what parameters does these VIH and VIL depend upon. And basically we found out that there is one particular ratio called as KR, that is the ratio between KN and KP, that is KR is equal to KN by KP, and this particular ratio is in our control and actually affecting these values VIH and VIL. Okay, and rest of the other parameters are more or less constant for any given technology node. Okay, and then the equation for VTH, and remember the various conditions for calculation of these parameters. For example, in these cases VIH and VIL, we had this condition that the slope is equal to -1. Okay, so we inserted this condition in the derivation of these parameters, and here also, right? And similarly the condition for VTH is that VTH is equal to V in and V out. So when the input voltage is equal to output voltage, that particular condition is to be used for the derivation of this threshold voltage. Okay, and we know that at these condition both the devices are in saturation mode, so we'll use the saturation current for NMOS and saturation current for PMOS and then derive it like this. You will get the equation for VTH like this. Again, look at this parameter KR ratio. This is again affecting this particular parameter VTH. Okay, so basically the thing is that the way we can affect the design of CMOS inverters, or way we can affect the VTC characteristic for the CMOS inverter is by taking control the ratio, the value of the ratio KR, which is when you go inside it, we will see that it is nothing but the way how do we control, what do we take the value for WIN ratio for NMOS and WIL ratio for PMOS. So basically it all comes out in terms of the ratio of WL, that is width by length of the channel or the gate. Okay, so again this is the simple structure, PMOS and NMOS, and this is the VTC characteristic between V out, output voltage, and input voltage in the x-axis. Okay, and remember here, look here, the VDD or VTH or VOH is taken as 2.5 voltage, the power supply, and this is the ground. Okay, 0 voltage, it starts from 0 and goes up to 2.5 voltage. So for this case the power supply is 2.5 voltage and not 5 voltage. Okay, so again I'm saying that this power supply will change with respect to the technology adopted for that particular inverter. Okay, so it may be in some cases 2.5 voltage, it may be in some cases 3.3 voltage, it may be 5 voltage. So do not worry about that, just keep in mind that there is a there would be some sort of power supply voltage and there would be one ground here, and when you plot the curve between input voltage and output voltage, it will come out to be like this. Okay, and there are various regions. Okay, like here for this NMOS is off, PMOS is in resistive or linear region. Okay, and at this point NMOS is in saturation and PMOS is in linear or resistive region, and we know that at this threshold, inverter threshold voltage, both of the devices are in saturation, and then as we move forward, NMOS goes into resistive or linear region and PMOS goes into saturation, it remains in saturation, and then it ends like this, NMOS goes into linear region and PMOS goes into off mode or cutoff region. Okay, so this is how the respective mode of operation of the devices changes as we travel through the VTC curve. Okay, and this thing we had seen it many a times early also, so that I am giving it here so that it becomes again more it becomes easier for you to know the things, to grasp the things. It becomes even more easier to imagine how the curve, how the this inverter is working. Okay, now look at here again, I'm showing this particular VTC here. Now in this case this power supply is taken as 5 voltage. Okay, so again do not worry about this. Okay, so for this case, for this particular example, VDD is equal to 5 voltage, the threshold voltage for the inverter VT naught N is 1 voltage, and threshold voltage for the PMOS is -1 voltage. Okay, so this is 1 voltage and this is -1 voltage, so basically their magnitude are same, but this is of negative polarity and this is of positive polarity. Okay, and Kn is equal to Kp, so the respective K parameters are taken as to be equal. Okay, now one interesting parameter here is the mapping of this drain current. Okay, on this VTC characteristic. Now when we go back to this VTC characteristic curve, we see that at this point one device is off, the other device is in resistive or linear region. At this point, as we move towards VDD along the x-axis, okay, at this point one device is in saturation, the other device is in resistive. Okay, as we move forward, we see that at this point here, both the devices goes into saturation mode. It means that both devices are giving their maximum amount of current. So here PMOS is also in saturation, NMOS is also in saturation. So both are in saturation, both are supplying their maximum maximum current. Okay, and here PMOS remains in saturation, but NMOS goes in resistive linear region. So PMOS still gives maximum current, but NMOS restricts this amount of current, and overall, because the branch is same, so current gets limited by the mode of operation of NMOS, and the current value decreases. So what I am trying to say here is that the amount of current that flows through this branch between VDD and ground will be depending on the mode of operation of this particular device PMOS and this particular device NMOS. Okay, and this will be maximum. The current through this branch will be maximum when PMOS and NMOS both are in saturation mode and they are able to pass through them the maximum amount of current that is possible. Okay, so when both are in saturation, that is at this point, when at this threshold point of the inverter, okay, the current reaches to its maximum value, and then it starts to decrease as we move forward, and it also starts to decrease as we move backward. Okay, and this current will be maximum at around this point of operation. Okay, and this is what's shown here, is that this drain current curve is maximum, okay, at this point. Okay, and this is the point when both the devices are in saturation mode. Okay, and the current becomes maximum, and as we go backward it starts to decrease. Okay, and also as we move forward it starts to decrease like this. Okay, so the point here is that the drain current will be maximum at the threshold voltage of the inverter. And why it is so? Because both the devices are in saturation mode, so both are conducting their maximum amount of current. Okay, and because of this, the current flowing through them becomes maximum for any given voltage between VOL and VOH. Okay, so this is how the drain current will look like when it is plotted against the VTC characteristic. Okay, and we should know that why it is maximum at this point of time, at this point of voltage. It is because at this voltage of input, at this threshold inverter threshold voltage, both the devices are in saturation and both are conducting to their maximum value. Okay, and it is because of this the curve for the drain current looks like this. Okay, so some important points: if the input voltage is either smaller than the threshold voltage of the NMOS or larger than VDD plus VT0 P, we know that if the input voltage is smaller than VT0 N, the NMOS will be in cutoff, and if it is larger than VDD plus VT0 P, the PMOS will be in cutoff mode. Okay, so if any one of the device is not conducting, is kind of open circuit, the current will not flow through the branch. Okay, and we say that it does not draw any significant current from the power supply. So power supply gets disconnected from the ground, and because of power supply the current becomes negligible or almost zero. But there is an exception that for small leakage current and threshold currents are still flowing, and but these are very less in magnitude, but still they become significant when we scale down the devices to very small sizes. So when the size of devices goes on becoming smaller and smaller from micrometers to nanometers. Okay, so when we go from micrometer into nanometer regime, okay, then these things becomes more and more important. Okay, but when the device is bigger in size, we can very well ignore these leakage and threshold currents. Okay, and during low to high and high to low transitions, that is the regions for B, C and D, the current is being drawn from the power source. Okay, and it reaches its peak value when Vin is equal to VTH, that is the threshold voltage for the inverter we had just seen. And why it is so? Because at this point both of the devices are in saturation mode and both of them are conducting to their maximum peak value. Okay, So basically we had seen this is coming from the equation for VTH. So when we manipulate it, when we just rearrange this, we can get the equation for Kr. So under root 1 by Kr would be equal to this term. Okay, so from this we can get the equation for Kr, that is equal to Kn by Kp. We know this ratio, and this becomes this VDD plus VT naught P plus VTH by VTH minus VT naught N whole square. Okay, so and we know that this switching threshold voltage of an ideal inverter is defined as this VTH for ideal inverter is nothing but VDD by 2. Okay, so ignore this S is extra here. Okay, so I can write here, just ignore this. Okay, so this is VDD by 2, that is if it is 5, VDD is 5, it becomes 5 by 2, that is 2.5 voltage. So somewhere in the middle, okay, for the ideal inverter. And putting up this equation, this condition in this equation, okay, we can get the ratio for Kn by Kp for an ideal inverter. That will come out to be around 0.5 VDD plus VT naught P by 0.5 VDD plus VT naught N whole square. Okay, this equation will come for the Kr. This is nothing but Kr for an ideal inverter. Okay, so putting up the condition for an ideal inverter in this equation, we will get the equation for Kr for an ideal inverter case. Okay, and if we take the value of VT naught N to be equal in magnitude to that of VT naught P, that is, just in the previous case we had seen that VT naught N was 1 voltage and VT naught P was minus 1 voltage, so their magnitude was equal, their magnitude were equal. And if the magnitude is taken as a common VT naught parameter, okay, and putting up this condition in this equation, okay, you will get that Kn by Kp for a symmetric inverter becomes equals to 1. Okay, so remember that for a symmetric inverter, the ratio, that is Kr, becomes equals to 1, is equal to 1 for a symmetric inverter, right? And for an ideal inverter, the equation for Kr is this one. Okay, right. And we know that we have seen this diagram earlier, but again let's go through this. That we know that Kn by Kp is nothing but Kr. Okay, and put up the expression for Kn here, that is, we know that Kn is mu n C oxide W by Ln, and Kp is mu p dot C oxide dot W by Lp. Okay, and cancel out this C oxide here. Okay, assuming that C oxide for both of the devices are equal, okay, we are left with this ratio. Okay, we are left with this ratio, and for a symmetric inverter, we know that we have just seen that Kn by Kp is equal to 1. So insert that condition here, and you will get that W by Lp should be equal to 2.5 times W by Ln. So what does this indicate? Since this is a very important conclusion that comes out here. Okay, so we basically know that this W by L defines about the size of a particular gate or a particular MOSFET, particular device. Okay, so it says that the size of the P MOSFET should be approximately equal to 2.5 times the size of N MOSFET. Okay, for designing of any symmetric inverter in this case. Okay, and what is a symmetric inverter? So symmetric inverter is any inverter having a ratio Kr equals to 1. Okay, so look at here in the diagram, this is the curve for Kr equal to 0.25. Okay, and this curve is for Kr having a value of 4. Okay, and this middle one is having a ratio, having a value of Kr equals to 1. So this is the case for a symmetric inverter, and SYM. Okay, so you understand this is symmetric inverter, and you can very well differentiate this thing from other types of inverter VTC characteristic, that what does a symmetric inverter means. Now a symmetric inverter would be such, which would be having a VTC characteristic that will look like this. So we can see that this will come out and this will cross the cut intercept this x-axis somewhere around 2.5 voltage, okay, which is actually equal to VDD by 2, where VDD is nothing but 5 voltage. Okay, so a symmetric inverter would be having some sort of symmetricity. It will be symmetric around VDD by 2, where this is the first half portion that will be equal to the other half portion that will lie between this VTH and the VDD. Okay, so any VTC characteristic having this portion equal to this portion, okay, can be called as a symmetric inverter, and this is not applicable for this, so we cannot call this VTC as, and this VTC also the case for a symmetric inverter. Okay, so this is how we can recognize just by looking at a VTC characteristic that whether this VTC is for a symmetric inverter or not. Okay, and when it comes to the calculation of the noise margin, okay, and put up these conditions in VIL and VIH. Okay, so this is the case for VIL and this is the case for the VIH. Put up these conditions into these equations, and knowing the fact that VIL plus VIH becomes equal to VDD, when you add this VIL term with VIH, okay, it will come out to be actually equal to VDD. Okay, so the noise margin low, we know that this is equal to VIL minus VOL, where VOL is nothing but 0 voltage. Okay, so it actually becomes equal to VIL for a CMOS inverter, the low noise margin, and the high noise margin, that is equal to VOH minus VIH, and knowing that this VOH is equal to VDD, it becomes VDD minus VIH. Okay, VDD minus VIH, and when you put up this condition, this particular equation in this condition, okay, so this will come out to be VDD minus VH, VDD minus VH, that is, this will come out to be VIL. So for a symmetric inverter, we can say that the noise margin low should be equal to noise margin high, and that will be equal to VIL. Okay, this is the case for a symmetric inverter, and this is not applicable for any general inverter. Okay, but our focus, our effort will be such that to design a symmetric inverter, so that we can have more benefits in terms of the propagation delay things that we will see in the coming classes. Okay, so this was about CMOS inverters and the various things, the various derivations, and some designing constraints, some designing point of views related to symmetric inverters. Okay, and then okay, there is one example taken from the book Kang here. So let us see. So in this thing they have told us to calculate noise margin low and noise margin high. Okay, and given that this VDD is 3.3 voltage in this case, look at this, the power supply is 3.3 voltage. Okay, VT naught N is 0.6 voltage and VT naught P is minus 0.7 voltage. Okay, so magnitude of VT naught N is not equal to magnitude of VT naught P. Okay, take this point in note of, take a note of this point. Okay. And Kn is taken as 200 microampere per volt square, and the value of Kp is 80 microampere per voltage square. Okay, so will it be the case of a symmetric inverter? Definitely not. It's not going to be a symmetric inverter, by looking at these values. Okay, but what will be the value of noise margin low and noise margin high for this case? So you will go through this, solve for the value of VIL here, VIL. Okay, it will come out in terms of V out. Okay, then again substitute this back into this equation for VIL, and you'll get the equation. The value for V out is 3.14 voltage. Okay, and from there you will get a value of VIL to be 1.08 voltage. Okay, again you will have to calculate the value of VIH, because you know VOL 0 voltage and VOH 3.3 voltage, that's clearly defined. Okay, so the thing is to calculate VIL and VIH mainly for a CMOS inverter. So again VIH, calculate here, use the formula, it will again come out to be in terms of V out. Okay, again put back this in the previous equation. You will get a quadratic equation, solve for it to get the value of V output. Okay, so from this value you will get the value for VIH here, and once you know the value of VIL and VIH, you can very well calculate the noise margin low value and the noise margin high value. So look at this. In this case, the noise margin low is 1.08 voltage. Okay, and the noise margin high is 1.75 voltage. Okay, and since they are not equal to VIL, so it is not a symmetric inverter. This is look at here, calculate the noise margin of the circuit. Okay, notice that the CMOS inverter being considered here has KR 2.5. so KR here, that is the ratio of Kn by Kp, Kn by Kp here. Okay, and this ratio is not equal to 1, actually is not equal to 1 here. So we say that this is not a symmetric inverter, this is an asymmetric inverter, so hence it is not a symmetric inverter. Okay, so for this non-symmetric inverter, the value of noise margin low comes out to be 1.08 voltage, and the value of noise margin high comes out to be 1.75 voltage, right? Okay.